This lecture represents our last talk about methods for phylogenetic analysis, and we're going to talk about Bayesian analysis. Bayesian analysis is the most recent method developed to estimate phylogenies and try and find the best sets of relationships among organisms. If you have had some background in statistics, you may have come across Bayesian analysis. However, it is a little bit more of an advanced method, one that's used widely outside of phylogenies, but in more advanced applications. So unless you've had a more advanced statistics course, you may not have had it, or you might have only had it mentioned. We're not going to spend a lot of time learning all of the details, learning the mechanisms, learning the in-depth theory of Bayesian analysis, but we are going to give you an overview so that you understand in general terms how a Bayesian analysis works. To put Bayesian analysis in its proper context, it comes along, again, fairly recently and is a very, very widely used, maybe the most widely used method for phylogenetic reconstruction now. And it was developed largely as a response to the computational intensity of maximum likelihood. So if you'll remember, maximum likelihood was a response to not being able to implement models of evolution into parsimony analyses, which either treat everything identically and don't allow us to use anything about our data to help us infer differences in weights or differences in probabilities for our different evolutionary events, or we can change them and give them different weights, but there's really no good objective reason for what weights we would give them. And so along comes maximum likelihood, implements a model of evolution, but the big trade-off, the downside of maximum likelihood, is that it's very, very computationally intense. So we're taking 10 or 12, 20, 100 times as long to do our evaluations because of this computational intensity of the maximum likelihood. And so people begin looking for a method that can implement a model of evolution, use statistical tests to determine whether or not a phylogeny is better than, say, your average phylogeny or a specific other hypothesis. And so we want to be able to do that, but we want to be able to do it in an amount of time that is reasonable. Particularly as our data sets are getting bigger and bigger, we're able to gather lots and lots of genetic data. And so Bayesian analysis was largely an answer to that. But it is also a different theoretical approach, albeit with using statistics and models of evolution, but it is a different theoretical approach than maximum likelihood. So let's talk in general, and maybe this would be better with a little bit of a normal distribution. In fact, let me put one in. So I'm just going to find a quick normal distribution. And I'm hoping that this is very basic for all of you, that you've had this maybe even in a very early course. Let's see how this one looks. Oh, I'm going to have to give me one more sec here. Okay, so this graph represents 4 different possible normal distributions, and not all character traits look like this, but many do. So for instance, if we were to look at height in humans, it might look something like this blue distribution, where we have most people are around 5.5, 5'7", depending male or female. We could maybe have slightly different distributions if we distinguish gender. Or sex, I guess is a better word. But if we were to distinguish them, we might have slightly different distributions, but most people are going to be around the middle. We have a low number of individuals, which is represented on the y-axis here. A low number of individuals that are very, very tall, and the more extreme you get, the fewer individuals you have that are that height, and a few that are very short, right? And so if we were to pick any height at random, and let's say we pick 10 people at random, and if we pick 10 people at random and they are all in this area, maybe we have an inclination, we could even put some numbers of probability on it, that our selection is not really truly at random, because if we had 10 individuals, we would expect them to be kind of from all over, but probably because our numbers are so high here, most of them would be here. But if 10 people chosen supposedly at random are showing a very different distribution than what we have, then we do a statistical test to say, well, how certain are we that this is a non-random selection of individuals? And that's an important and powerful thing that we can do. But we might have another one. So let's say we look at maybe, and I don't know whether these distributions would really look like this, but let's say we look at average intelligence, which is difficult to measure, but IQ, just as a rough estimate. Average IQ score, and we have a few individuals that have high IQ scores, but most individuals, there's kind of this very flat curve. So this yellow one might represent average IQ of humans. And there's a much flatter distribution. And so we would expect, again, if it was a random one versus a biased or skewed distribution, we would expect a different probability of outcomes if we had this curve versus this one. Now that's terrific if you know what the population curve is. And so you can get that by sampling, or if you've got large data sets, maybe even you don't need to rely on sampling. And depending on how thorough your sample is, that's going to impact what you can say about a subcategory, a supposedly random, or if you're trying to determine if it's non-random. So that's an overview, and it's a little bit of a complex idea, but once you start getting into it, if you've had a basic statistics class, hopefully you're comfortable with that. Okay, so just be aware of that we would need some idea of the distribution of traits, and then we could look at any sample out of that or any result and determine whether it was a unusual sample or whether it was what we would expect based on our known distribution of traits. Okay, so we'll come back to that, but that's a little bit of review of a basic overview of statistics. That's statistics in 2 minutes. Okay, now we're going to make some distinctions between Bayesian analysis and maximum likelihood analysis. And we're going to address this question, and we'll come back to it at the very end of our next discussion to determine the answer to it. But just keep this in mind. So the first major difference between a Bayesian analysis and a maximum likelihood analysis is the way that we calculate the score or the probability of any hypothesis. So again, reminder, a hypothesis in this context is simply a phylogeny. And the data is that matrix, usually of genetic characteristics, but that alignment of characters where we've made them in homology statements in the different columns. And so when we were doing maximum likelihood, we calculated a probability score that was the probability of our data given a hypothesis. With Bayesian analysis, we flip that around. So it's a slightly different calculation, and we're not going to get into all the guts of it. Again, it's a fairly complex one. You don't need to know exactly how it's arrived at. But notice that we've flipped these values. So our probability scores, what is the probability of this hypothesis, this phylogeny, given this data? Which for most people is a little bit more intuitive way to calculate it. But it still is a fairly computationally intense calculation. But the key to a Bayesian analysis, if you don't have to do this quite as many times because there's a slightly different approach. Now, before we talk about that slightly different approach, let's talk in general about our probabilities and our probability distributions. So remember back here, if we have a known probability distribution, then the statistical analyses for any subcategory, any candidate result or group of results is fairly simple because we can simply compare what we've got with how many we have to our known distribution. And of course, the bigger your candidate sample population is, then the closer we would expect it to adhere to this distribution from the population. But that's assuming you know that distribution. So what happens when you don't know, right? So let's say we don't know anything ahead of time, right? So let's say, and here's our example. Let's say that you are going to shoot a number of arrows at a target. Now, if I have some prior knowledge, and this would be knowing something about the probability of outcomes, right? If I knew that you were a really, really good archer, I could probably draw a probability that would mean you've got a low chance. This is only 2 dimensions, but let's say we're saying how far away you are from the bullseye, with right here being as close to the bullseye as possible. If I know you are a very, very good archer, well, let's say 0. Let's say this is at the bullseye, and then the more we go around here, the farther away from the bullseye we are. So if I know you're a very, very good archer ahead of time, I might predict something like this, right? Where most are going to be very, very close to bullseye, and then it's very unlikely that you're going to have something far, far away, right? So that's helpful. That is an informative, what we will call a prior probability, right? If I know that it's very likely for you to hit the bullseye, and this is very helpful for us. And so then I could predict an outcome of, I think this is 10, or that's more than that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's a random number. But I would know that if you had 11 shots, most of them are going to be pretty close to the bullseye. So that's helpful. Now, let's say I don't have any idea at all. Let's say I don't know anything at all about the archer. I don't know if they've never held a bow and arrow in their life before, or if they're an Olympic class archer. And so I don't have any idea at all. So maybe what I would do then is my prior probability would actually be more of a flat. Originally, I'd have a flat curve where I say, I don't know if they're going to get close or far away because I don't know anything about their talent. So we would then maybe run a single outcome. And this is the results from our first trial. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is it still 11? I don't know why they chose 11, but you could choose any number. And again, the larger sample, the better for our statistical comparison. But let's say this is the result. Now, originally, you look at that and you're like, oh, that's a really bad archer. But actually, when you think about it, this is not a bad archer. This is probably a good archer who's not trying to hit the bullseye, right? Because every shot is very, very similar to its distance to the bullseye. So this is actually useful also, and it tells us something about the skill of the archer and maybe also the intention of the archer. Is the archer trying to hit something specific, or are they trying to make a nice round ring around the bullseye? But this is helpful also because it's a very clear pattern. But something like this, of course, would be unclear, meaning that, and this is not very helpful for us in making predictions about what's going to happen next, because this is somebody who is not good at all. Okay, so someone who is good and shooting for the bullseye, that's a useful probability, and we've got information from it. Here we have somebody who is good but not trying to hit the bullseye, trying to get at a specific distance from the bullseye, and that's also useful. And after we ran these 11 instances, we'd have a pretty good idea of what was going on in the system. And if the rules didn't change, the intent of the archer didn't change, we'd be able to make some pretty good predictions, at least about the distance away from the bullseye. And of course here, this is not very useful at all. This is not a helpful distribution for us if we're going to use this. So we are going to introduce this idea of a prior probability. And in Bayesian analyses, a prior probability is a starting point. If we have some information to start with, then maybe we can come up with some ideas about the rules of the system, about predictions, about how we would go about analyzing our data. Now, this is not a very useful prior probability because it doesn't give us much information. Maybe we know there's a low chance of getting really, really far away from the bullseye, but within our bullseye, it's very random and we're not going to be able to say much at all. But this, right, and this are useful prior probabilities. Now, we start with a prior probability, and then in a Bayesian analysis, what we do is we begin to look at outcomes, at results. And then, after a certain number of outcomes, we reevaluate our initial hypothesis. So if this was our initial starting prior probability, we think the person is very good at aiming for the bullseye, and then we get a bunch of results like this, we're going to have to change our original prior probability. And so the Bayesian analyses works in iterations. We do it over and over again. We start with our best guess. And maybe there is no good guess, and so it's very flat with nothing. But we start with our best guess, and then we run the analysis a little bit, and then we pause it and reevaluate our prior probability. So this outcome, the set of results, is known as now a posterior probability with gathered data, right? And we then reevaluate our initial probability, and now our posterior probability, right, which is our first set of results, would be reevaluated into our prior probability. So posterior becomes our new prior, and then we run the analysis again. And then we pause, we reevaluate our probability distribution, and then we run it again and again, and we go through iterations of this. So the useful thing about this approach is we don't have to know anything about the data. So if we know nothing at all, we maybe make a very broad assumption about the outcome of results. And then we run it a few times, and then maybe we can adjust and say, oh, look, the results are actually a little bit more narrow. The probability distribution is more narrow than we had originally thought. And so we can use this to influence our next round of analyses, and we do it over and over and over again. So we calculate a posterior probability distribution. It's based on our prior one, but it's informed by this set of tests or analyses that we've done. And we get a brand new probability distribution, and this posterior one becomes our new prior, and we do that again and again and again. Okay, so that's a helpful way, particularly if we don't know what to expect from our distribution of outcomes. And so let's talk very generally before we end this discussion about a phylogeny. What would we expect from our outcomes? Now, if we have very good informative data, we might expect a very small number of trees to have a very good overall score. And so we might expect, in fact, let's kind of sketch out a couple of possible outcomes. All right, so here's a graph showing tree scores. And let's say that this, on this side, is a very good tree score. So this is not a very, it's just a very bare bones graph, right? So let's fill it in a little bit. So let's say at this end, we've got very, very good tree scores. And then down here, we've got very bad tree scores. Now, what we might expect to see, if we want to find the very, very best tree overall, if we've got very good data that, you know, there's a good, strong phylogenetic signal and not much else, we might expect that most of the trees are going to be in this very good range, and there's a very few that are at the very best. So we want to find the one or two trees that are just a little bit better than the next ones, but there are lots of trees that are relatively good, okay? And so if that's our assumption, then we would expect after a first round that we would have, you know, mostly good, maybe some in the middle range, and very few bad trees. But if, on the other hand, we have a distribution like this, and maybe this is very saturated data where most of the trees are in the middle, it looks a little bit more like a normal, and there are only a very few trees that are very good, then our first round of iterations, we might expect to have most of our phylogenies in this area, okay? So, and of course, if most of the trees are very bad and we don't have any very good trees, that's probably not real great data to analyze, okay? So we don't know, though, ahead of time what our distribution curve looks like. Does it look like this? Or does it look like this, being fairly skewed? We don't know ahead of time. And so what we can do is we can do a Bayesian analysis. We start with our best guess, with an initial hypothesis about this distribution. And maybe we make a fairly flat curve if we don't have much. And then we run a few iterations. Now, in a phylogeny, we have not only the distribution of trees to think about, but we also have a model of evolution. And remember, there was this little bit of catch-22, that it's difficult to choose a model of evolution until we have a phylogeny. But the whole reason that we're trying to pick a model of evolution and the parameters for that model is that we want to figure out the phylogeny. So that's our paradox. In our next discussion, we'll talk about the process, the next steps in the Bayesian analysis, and we will talk about our model of evolution and how we implement that in the analysis, and how we even allow the parameters for that model of evolution to change as the analysis progresses.